Thank you all for having me today. I will be presenting, like I said, versatility and cost savings through the modernization of the wax room. I want to thank the customers that we were able to collaborate with, the ICI and all of my team back home. This is certainly not me, but a big effort to get to this point. TechCast, Lamathermic, an additional customer who is happy to share their information for the education of everybody here, but did not want their name shared. As we progress, our customers are demanding more of us out of our castings, out of our products. And it's my belief that there's a lot of opportunity in the wax room, and we've seen that quite a bit. We've had a lot of success in aerospace and medical, and we've talked about that a lot on this stage. Over the last years, we've really been focusing on the commercial foundry, the high mix, and how do we help to elevate. And as you know, whenever you do a solid improvement, it really opens up the opportunity to see other bottlenecks throughout your entire facility. And I'm looking to demonstrate, or I'm hoping that by the end of this, you see how by improving the quality of the pattern and assembly going into your shell room, you're going to end up with a lot of gains downstream and a clearer picture on what to improve downstream. So this, I believe, is the beginning of the improvements to a continued improvement journey. So today I'll show you how we can improve or increase your injection capacity 20 to 50%, reduce the number of assemblies required by 20%, reduce the amount of shell and metal required to create the same number of castings, improve your operator efficiencies, not only in the wax room, but throughout the entire foundry. And most importantly, reduce the cost of the casting going out the door. And if you're running a foundry or in a foundry, what you do with that savings is up to you. So for this study, everyone we worked with had a manual equipment and manual assembly stations. And we worked with them with legacy parts that they had, and we brought their tooling into our facility, where in collaboration with them, we brought their tools in, we aligned it with our die standards, our handling standards. We did a baseline to understand what the capability was running in their facility and their site, make sure we understood what they were truly getting today. Cleaned and repairs the tools as required, quantified the scrap, and once we had a good, solid injection that was running the way we wanted it, we then moved on to the assembly, where we eliminated the rework, increased the densities, again, in collaboration with our customers. We kind of came to what we wanted to try to achieve in this first. And then from there, we shipped them the finished assembly, and we inserted it into their shell room. And that's really the exciting part, is all the gains that we see downstream. So as I said, our customers started with capable machines, but the process is controlled by the operator, right? And this is common that we see this, that you have a machine, it's a manual machine, and you have to adjust the inputs based off the sheet. And no matter how good your standards are, it can only be as good as your operators are at repeating. Some operators, as we know, are incredibly good at this. Some are not, and certainly operator to operator or machine to machine, there's variation. And it's hard to get visibility into that. One of the tools we use is our 2020. The 2020 is a tool that we use, and we can use it for calibration and also to get a visual representation of what's happening within the injection process and happening in your tool. This can be connected to any machine in the world, and it gives us that same graphical interface that we get on our modern equipment. From there, we're able to take that and bring it onto our piece of equipment, replicate what we're seeing in the foundry, again, get a baseline, and then on our modern machines, combine that with our comprehensive standards in-house and really get some good gains. To give you an example of what that is, and this is something that we see regularly when we connect our equipment to our customers' machines. Again, this is not to say that the machines aren't capable or your operators aren't qualified, but it is often a lack of visibility into what's actually happening in the machine. And what you see here, it's really hard to read on the scale, but we're actually doubling the amount of time it takes in some cases. So this is just a machine where you walk up to it, you start running it with the tool that's on it, doubling the amount of time that it takes to fill the die. This, again, isn't the machine is doing what it's supposed to do, it's doing what we have asked to it, but due to the variation in the material, you're getting a different result, which means that your filling profile is changing from injection to injection, which is why we often see that the first couple parts are bad, or the last parts, or my operator went on a break and it got something different. It's not the same today as it was last time. Often it's a fundamental issue in setup and understanding of what's happening in the machine. And this is where that visibility really helps. Once optimized, you end up with a graph that looks more like this. You can see there's the same number of injections, but we're getting the same consistent injection every time, again, starting on a cold machine. For this, we took 5 part numbers, production volumes between 250 and 15,000 parts. Small parts, they'd fit in the size of your palm of your hand. And we're going to start by doing a deep dive into this part in particular, and then we'll review all 5 parts and see how kind of the similarities and differences running from part to part and how that looks. As I said, the first thing we do is we create a baseline, and we found that our customer was actually getting a scrap rate of around 52%. Their parts per hour that they were producing was 257 parts per hour, and they were only getting acceptable parts of 121 due to that scrap rate. And it is easy to say, not in my shop. I ask you, make sure, are you counting your scrap? What are the rules around remelting a pattern? It is very easy to underestimate the cost of that wax and to just build that into your cost, remelt it, throw it in the bin, break it. It's very hard to come back and capture that at the end. And given the cost of some of the castings that we're producing, it feels inconsequential. But when you have a scrap rate that high, you are inherently going to miss some of those, and they're going to get into your system. And how many of those are getting misqualified and misrepresented as to where that defect came from, and how many of them are getting reworked, if you're allowed to rework it, downstream, adding excess processes and excess cost to every single part. As you can see, once we optimized it, we were able to bring the scrap rate down to 4%. We increased the throughput to 322 parts per hour, so we were able to run it faster. And we had 310 parts at the end of every hour that were acceptable to go into the stream. This particular tool was an 8-cavity tool. Because of this reduction in parts, that meant that we had to run 1,152 less cycles than our customer did to make the same number of parts that got assembled. What does that mean? Do the math. Works out to 17 hours saved in one production run of one part number. From there, we took the part and we put it onto our automated injection cell, so we didn't have to have the interaction with the operator as much, and we focused on the assembly. This is our 2012 automated assembly machine. I think some of you have seen it at this point. It is an assembly machine that's focused on one part at a time. It uses a sticky wax, and it has some really nice features to make it very easy for operator setup and focused on repeatability and quick changeover. Why do we want to automate and optimize the assembly? It allows us to optimize the part spacing, and the flexibility allows us, and this machine's designed, to allow us to run at your optimal, the machine can run at your optimal production flow. How many assemblies are you trying to put through of what, and in any quantity, because it's just a quick changeover. Increase total throughput through the facility, no damage, and really decrease the amount of training required in assembly so that we can help our employees have more value added and be trained in other areas so that they're more flexible throughout the facility. And we did a full paper on that last year as well. So for this test, we ran 13,500 parts for this one part number. We had multiple assembly variations. We created 5 assemblies of an 80-part variant. So this represented and duplicated the spacing that our customer was currently doing manually. From there, we went and created a 90-part variant by adding one more row of parts, and we built 140 of those to go into production. And then we did a forward-thinking baseline to say, what's the moonshot? And we did the same 9 parts per row, plus we added an additional 8 parts per side. So a total of 150 assemblies that we put into our customer shell room. And it's worth noting that the first recipe we had to create, the first time we had to train the robots, we're able to do it in under 30 minutes. The second and third variant was just tweaking a recipe, and it took an additional maybe 5 minutes. So we have total programming time in this is under 40 minutes. And from there on, if I wanted to go back to the shop and run any of these, it's just as easy as selecting a recipe, loading it, and having the machine do it. The standard lives in the machine. Of course, this is the time where we get asked the question of, how can you go that close, or we can't go that close? And I would say that historically that's true, but it has to do with the variation of a human. If you go and measure manual assemblies, you're commonly going to see an 1/8 to 1/4 of an inch plus or minus in variation. Right? So that's not really the capability of the shell, but really the capability of the operator that's assembling it. With the automation, we're now able to look at this as a complete assembly and a unit that is repeatable. You can see that was a 0.125 spacing is what we're using. And I ask you, so it's easy to say we can't do that. But if you look at this, and if your customer comes to you and says, I want you to create this geometry, would you turn the part away? I see one person shaking his head no. And if you're uncomfortable with that, what's a geometry in the alloy that you're talking about that you're shelling today? Because that hole was already being shelled and was already being cast, but it's a lot smaller than their original spacing. Again, it's the consistency due to the automation. Now we're talking thousandths of an inch, and an assembly looks more like a machined or an injection component as opposed to an assembly that's lots and lots of variation. That's all great. What does that mean when we go downstream? So we reduced our assembly time by 53%. We saved in assembly man hours over 44.5 hours. We decreased the pattern spacing, again, in alignment with our customers. Reduced the number of assemblies by 19 or 12.5%, so 19 less assemblies that we had to even make, which means I'm using 19 less pour cups. I'm injecting and assembling 19 less runners, which of course gives me a small wax gain as well as time. We take that and into the shell room, 19 less assemblies, 6 layers of shell. We're saving 114 dips, wear and tear in the robot. We're increasing capacity in this particular shell room by almost 12%. And I ask you, what's 12% capacity in your shell room worth? This is 160 mold capacity. We're assuming it takes a minute to load and unload, so you're saving about another 38 minutes of labor. And we have 0 part fall off because the welds are stronger than the parent material. And what we have found over and over again in doing this is what we've always thought of as a weakness is really a strength. And the shells are stronger, and it's worth noting that all 3 of these variants produce all good parts. So moving forward, we'll be able to do the 106 part variant if our customer chooses. That bridging and the reduction in runners leads to 826 pounds of shell that you don't have to use. That's 826 pounds that doesn't need to be mined, it doesn't need to be transported, it doesn't need to be purchased, and it doesn't need to be mixed. Again, for the same number of parts. We saw almost a 3% increase in our pour ratio. You can see down below that red box, 106 part variant has an even better pour ratio, makes sense. We're saving time in shell cleaning. Mostly this is just we're cleaning less shells, right? Our customer now, there's 19 less shells to clean in your water blast or knock off. 19 less trees to cut off. What was really nice in this particular example, the operators doing the cutoff actually came to management and said, I don't know what you did on those, but the consistency made my job easier. It was easier to cut off, I had less scrap, and I was able to cut off closer to the part. The next obvious step is, once we get there, the foundry now can look at really automating cutoff, right? It's hard to automate cutoff when you have a warped runner or it's not square, which is going to, in turn, eventually lead to less grinding, less use of belts, all of those other good benefits. So with this, the total gains for this one part number, again, 13,500 parts were produced, reduced injection by over 40%, increased our assembly capacity over a human by 53%. We saved a total of a little under 70 hours, so pretty rapidly closing into 2 weeks of labor that we didn't have to spend. We saved 826 pounds of shell material, 638 pounds of metal that didn't have to be heated or poured or transferred. Increased capacity in the shell room of almost 12%. And we reduced the defects in the cutoff, wax, and most importantly, we improved our customer delivery, right? We got more stuff going through using the same amount of equipment, delivering on time, less inspection, less rework, less scrap. So what does that look like? So that's great. That's a good example. What does that look like when we're looking at 5 parts? So here you can see that we have all 5 patterns. Customer B is TechCast. I apologize, I didn't update that. You can see that we have a total reduction in every one of our assembly variants. I think it's really important here to see that we are doing this in very low volume runs. This customer, Lamathermic, they're only looking for this one part number. They were originally looking for 15 trees. We can do it in 12 trees, and they're getting the same savings throughout. And for us, with the ease of setting up this machine, the automated assembly, it makes more sense for me to automate the assembly than it does to have an operator do it, because now it's just a recipe, it's saved, it's less paperwork, it's less stuff on my network, it's less worrying about someone following that standard. The standard is loading the recipe, not making sure you set it up correctly every time. And I want you to imagine, these aren't 3 individual customers or 3 competitors. What if those are 5 parts that I own? If that's a family or a couple families, it looks like, what does that mean over the course of the year to convert 5 part numbers to automation? It has a potential to save you 20 to 50% in your wax room. Not a bad capacity increase. We're reducing the number of assemblies we need to produce in that 1 year by over 1,000. And we've saved over 34,000 pounds of metal that we didn't have to heat to make those parts. I'm not going to do the calculation on power savings because I would be wrong, but I'm sure that you all know how to do that well. And we're saving roughly 17% on average in our shell material to make these parts. So where do we go from here? Because we're getting stronger shells, our customers are looking to reduce the number of shell coats for these recipes, saving more shell. Run additional parts with smaller batches because we've proven out that we really can do it and it really makes sense, so why not, right? Just that fast changeover really is a game changer. More complex assemblies, so we've already started doing dual gate and multi-gate assemblies. All three of these customers are looking to bring automation in-house so that they can have this and they can do it across a wider swath of their products. And some of them are looking to automate their cutoff and grinding. So from there, if you're interested in participating in a study like this, we've done these studies with aerospace, we do these studies with medical, and now we're really doing it with commercial. If you have a part family that you want to know what this does, my contact information is in the QR code. And with that, if you have any questions, I would love to answer them.